Good morning everyone. My name is Abdullah Tayyab and today I will be presenting on error recovery in bottom-up parsing and its applications. This topic comes under compiler design and it focuses on how compilers handle syntax errors efficiently without stopping execution. In real-world programming, errors are very common. So compilers must not just detect errors but also recover from them and continue parsing. This is the structure of my presentation. First, I will be explaining about the bottom-up parsing fundamentals. Then I will discuss the LR parsers family, followed by errors detection and techniques, and then different error recovery strategies. Finally, I will be explain real-world applications and best practices. Introduction to bottom-up parsing. Bottom-up parsing is a technique where we construct the parse tree starting from the input symbol and moves upwards to the start symbol. It is also called shift reduce parsing because it works in two main operations, shift and reduce. Shift push inputs token onto stack, reduce replaces symbols using grammar rules. Basically, we try to reduce the input string step by step until we reach the start symbol. Advantages of this bottom up parsing, uh, they handle almost all programming language grammars. They work in linear time, that is big O of n. They do not use backtracking. And error recovery is important because a compiler should not stop after the first error. It should continue and report multiple errors in one run. LR parsers family, its types and characteristics. LR parsers are divided into four main types. LR, simplest, no look ahead. SLR uses flow sets. Look ahead LR combines states from efficiency. Canonical LR, most powerful but complex. As we move from LR to CLR, power increases, complexity also increases. Look ahead LR is widely used in real world tools like ACK and Basin because it gives a balance between performance and power. Error detection in LR parsing. Error detection happens when the parser checks the action table. If there is no valid action for the current state and input symbol, an error is detected. Error actual mistakes like missing semicolons and unexpected tokens and like that. At the time of error, stack shows what has to be been parsed, left context, input shows remaining tokens, right context. It prevents cascading errors where one mistake creates many false errors. Panic mode recovery. Panic mode is the simplest error recovery technique. Here I will explain step by step process. Step 1, error is detected. Step 2, parsers enter panic mode. And 3, discards inputs token. And 4, stops when synchronizing tokens is found. The synchronizing tokens are like, for example, like it is like a semicolon and blocked end, like flower pocket. And the advantages of these panic mode recovery is it is a simple, no infinite loops. Disadvantages are may skip valid code, less accurate. Phrase level recovery. Phrase level recovery tries to fix errors locally instead of skipping input. It modifies the input slightly to make it valid. For examples, adding missing semicolon, replace comma with semicolon, insert missing operator, like that. And these corrections are based on heuristics, meaning they are intelligence guesses. If not handled properly, it may create incorrect fixes. Error production strategies. In this method, we extend the grammar to include common errors. For example, we can add rules to detect missing semicolons. Working of these production strategy is add rules, error rules, parsers recognizes errors, displays specific messages. Advantages of these are very precious error messages. Disadvantages are makes grammar complex, cannot cover all errors. Forward move algorithm. The forward move algorithm collects information about the future input after an error. It tries multiple parsing possibilities simultaneously and continues as long as they agree. When parsers disagrees, when more context is needed, these forward move algorithm stopping conditions are happens. Key concepts of these forward move algorithm are it produces a weak valid fragment which helps in validating corrections. It improves accuracy by using forward context. Berg-Fisher method. This method tries all possible single token corrections. Types of corrections: insert, delete, and replace. It tests each corrections and selects the one that allows parsing to continue the longest. Uses two stacks, one for the correct input, one for the testing corrections. Advantages are very accurate and disadvantages are computationally expensive. Minimum distance error correction. This method finds the best correction using minimum edit distance. Operations are insert, delete, and substitute. It calculates how many changes are needed to fix the input. Here, the dynamic programming technique is used. Choose the correct correction with the smallest cost. Here, the real life example are similar to autocorrect in typing systems. Implementation in ACK and Bison. ACK and Bison provides a special keyword called the error token, which is automatically used when a syntax error occurs. When the parser encounters an error, it stops normal parsing, it replaces the current input with the error token, then it tries to recover using grammar rules. How recovery works internally. The parser pops elements from the stack until it finds a state where the error tokens can be shifted. This means the parsers try to go back to a safe state where it can continue parsing again. And if there is a syntax error inside a statement, the parser will skip incorrect input. Then it continues parsing from next semicolon. The real world meaning for this implementation in ACK and Bison is this prevents the compiler from crashing and allows it to process the rest of the code. ACK and Bison provides useful macros, resets error state, removes current input token, checks if parser is recovery mode. These macros gives developers control over how recovery behaves. Some important best practices are place error tokens at the end of production. Use it after terminal, not non-terminal. Avoid overusing it as it may hide real errors. Applications in robust compilers. Why errors recovery is important. Without error recovery, a compiler would stop after the first error. This is not practical because programmers would have to fix errors one by one. It wastes time and reduces productivity. Real world systems like GCC uses advanced recovery techniques to detect multiple errors, provide meaningful messages where clearly errors messages suggestions like did you mean. For example, if you miss a semicolon, it suggests adding it. Modern ideas like VS Codes, IntelliJ, like that. IDEs use incremental parsing. Errors are detected while typing. Feedback is given instantly. Design principles. A robust compiler follows these principles like early detection, praises location, meaningful messages, and graceful connotations. Impact statistics. Errors recovery can increase error detection accuracy up to 85%. Detect 3 to 5 minute times more error in a single run. Best practices and conclusion. Best practices. Choose the right strategy. Different techniques suit different needs. Panic mode simple. Phrase level better users experience. Minimum distance high accuracy. Always test with common mistakes, edge cases, to ensure the phrases behaves correctly in all situations. Avoid infinite loops. Recovery should always move forward input. Otherwise, phrases may get stuck. Provide clear message. Error message should be explain the problem, suggest possible fixes. Error recovery is essential in compilers designs. Multiple techniques exist with trade-offs. Context is very important. Error recoveries transforms a compiler from a simple translator into an intelligent system that helps programmers write better code. Thank you for listening to this video.